Okay, so in this problem, we are given the mass percentage of each element found in NutraSweet. We are asked to calculate the empirical formula and the molecular formula of NutraSweet. And unless you happen to have this memorized for some reason, we're going to have to actually use our empirical formula calculation methods. So let's get started on that. So let's zoom on in. Let's erase this marker. So first things first, I'm just going to label. First things first, I'm just going to label. Oops. Let me set this to draw. I'm going to label. Oh. Set up. Still stuck in typing mode. Give me one moment to fix that. Okay, perfect. So the drawing tool is now back all set. So let's now get started. Allow me to close and reopen this, and then we'll resume in one moment. There's a small glitch with the OneNote software. Okay, so we label the first element as N1, the second element is N2, the third element is N3, and the fourth element is N4. It does not matter what element you pick as N1, N2, N3, or N4. This is just to help us keep everything organized when we write out our mole ratios. So we know in general, we're going to need to write the mole ratio of each of our elements with respect to one other element. So I'm going to choose to write all of our mole ratios with respect to N1. So first things first, let's calculate N2 over N1, which represents the moles of what? What did we designate as N2? Hydrogen. So this is the moles of hydrogen per moles of what? What did we designate as N1? Carbon. So this is the moles of hydrogen per mole of carbon. I always like to put my labels because it helps me keep things organized. Now we know from our mole ratio equation, this corresponds to the mass percentage of hydrogen over the molecular or molar mass of a hydrogen atom times the molar mass of a carbon atom over the mass percent of carbon in our sample. And we can plug in some numbers for that. We can plug in some numbers. What is the mass percentage of hydrogen? 6.16. Yep, 6.16. So we're going to take 6.16%. And what is the atomic mass of hydrogen? Yep, about 1.008 gram per mole. Okay. Then we're going to multiply by the molar mass of carbon, which is about 12.01 gram per mole. And then we're going to divide by the mass percentage of carbon, which we established was 57.14%. Okay, perfect. We're going to now punch this into our calculator. So N2 over N1, which represents the moles of hydrogen per moles of carbon, is equal to, let's punch that in. So we have 6.16 divided by 1.008 times 12.01 divided by 57.14. And in this case, we get a bit of a complicated decimal, but we're going to write out this decimal as is for now. So we get out 1.284 moles of hydrogen per every 1 mole of carbon. And we'll leave this alone for now, okay? So this is where we're at so far. And I'll show you how to deal with this complicated decimal in a moment. Our next step is to write out another mole ratio. And the key feature of each of these mole ratios, we are always having our ratio with respect to N1, with respect to carbon. So the next element in our list is nitrogen. So N3 over N1 is the moles of what? What is N3? What did we designate as N3? Nitrogen. So this is the moles of nitrogen per mole of carbon. Okay, and now we're going to use our mass percent equation. It looks exactly the same as our first expression, except instead of using the mass percent and molar mass of hydrogen, we'll use the mass percent and molar mass of, nitrogen, exactly. So then let's plug in our mass percent of nitrogen, which is 9.52%. And what is the atomic mass or molar mass of a nitrogen atom? 14, yep. So about 14 gram per mole. Okay, the molar mass and mass percentage of carbon are the same. And let's now punch this into our calculator. So we have 9.52 divided by 14 times 12.01 divided by 57.14. And that in turn gives us another somewhat messy decimal that we'll be able to handle. Everyone following so far? Okay. So we have 0.143 moles of nitrogen for every 1 mole of carbon. Perfect. Let's do our final ratio calculation. So N4 over N1 is equal to the moles of oxygen per mole of carbon. And what is the mass percentage of oxygen in our sample? What is the mass percentage of oxygen? Yep, 27.18. So then let's plug in 27.18%. And what is the molar mass of an oxygen atom? 16. So we have 16 gram per mole. The molar mass and mass percentage of carbon remains constant. It's the same in all of these equations. So let's now punch this next expression into our calculator. So we have 27.18 divided by 16 times 12.01 divided by 57.14. And that in turn gives us 0.357 moles of oxygen per mole of carbon. Okay, perfect. We have our mole-to-mole ratios. Now our job is to guess and figure out the smallest common multiple, the smallest whole number that we can multiply each of these fractions by to give us a whole number. So let's zoom out a little bit so we have a little bit more space to work with. So we're going to rewrite our mole ratios, and we're going to do that with a little bit extra space. So we're going to make some extra space here. So let's rewrite each of our mole ratios. So let's look at the mole ratio of hydrogen to carbon. So we have 1.284 moles of hydrogen per mole of carbon. That's our first mole ratio that we've established. We have 0.143 moles of nitrogen per moles of carbon. Okay, I'm just reorganizing the data that we've already collected. And we have 0.357 moles of oxygen per mole of carbon. And now what we're going to do is we're going to take each of our numbers and we're going to play a guessing game where we're going to plug in different whole numbers into our calculator and see whether we can get any of the decimals to be converted into a whole number. That's our plan so far. Does that plan make sense? Okay. So 1.284, okay? So it doesn't fall under any of our common decimals. So I'm gonna try times 6, nothing. So in my calculator, I'm going to now try times 7. So times 7, we get a number that's within 0.02 of a whole number. So it seems like 7 is a reasonable guess because it gives us a number that's within 0.02 or 0.01 of a whole number. Does that logic make sense? So we just tried different multiples in our calculator. So I tried times 7, and that gave me a whole number, or something very, 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 very close to a whole number. So what I'm going to do now is I'm going to take each of my mole ratios, and I'm going to multiply it by 7 moles of carbon. I'm going to multiply each of our mole ratios by 7. Now, this may not fix all of my decimals, but it will fix many of them. Okay. So from our first expression, we get 9 moles of hydrogen. And we know we have 7 moles of carbon. Let's look at this second number. So we have 0.143. So we multiply it by 7, and lo and behold, we get out 1 mole of nitrogen. So 7 seems like a reasonable guess, right? Okay. Finally, we'll take 0.357, and we're multiplying it by the same whole number of 7. And in turn, and this is where things get a little bit interesting, we get 2.5 moles of oxygen per mole of carbon. Now, don't worry. We still have an out here. Have we made this problem simpler? Have we reduced the amount of decimals found in our mole-to-mole ratios? Yes. Now we only have 2.5. And how do we get rid of a 0.5? What do we need to multiply by? 2. So what we're going to do is we're going to take all of these mole ratios, and we're going to multiply them by 2. Does that make sense? Okay. So then, in the end, we get 18 moles of hydrogen, 14 moles of carbon, 2 moles of nitrogen, and 5 moles of oxygen. Okay, so that's our theoretical assignment. And now all we have to do is write out our formula. So C14H18 N2O5. Wow, that's quite a whopper. Let's now look up and let's identify our molecular formula. So this right now is our empirical formula. Let's take the next step and calculate our molecular formula. Does everyone understand this guessing process for the mole ratios? So you guess and you find a whole number to convert as many of your fractions into whole numbers. Then, if you have decimals or fractions remaining, you repeat this process. Does that make sense? Okay. So we're now going to look and see what information do we have about the molar mass. So the molar mass was given as 294.30. So let's go down and let's figure out. So our molar mass is 294.30. This is our molar mass. Okay, let's now, in order to convert from the empirical to the molecular formula, we're going to look at our calculated formula, and we're going to determine the molar mass of our empirical subunit. So we're going to add up the mass of each of our component elements. So we have 12 times 14 plus 1 times 18 plus 2 times 14, and then 5 times 16. So we're going to add up the mass of each of our component elements and compare our empirical molar mass to our given molecular mass. And this is a way to check your work. If the empirical formula is not related to your molecular molar mass in a whole number ratio, something has gone wrong in your first calculation. Does that make sense? So you really want to appreciate the fact that when you have the molar mass, you have an out. So we'll have 12 times 14 plus 18 plus 2 times 14 plus 5 times 16. And lo and behold, it's a perfect match. Yeah. So do we have to do anything special? Do we have to even calculate N in this case? Are the empirical and molecular masses different? If our empirical mass is 294 gram per mole, do we have to do any additional work, or are we done? You're done, exactly. In this problem, the reason why I gave you the molar mass is so that way you can check your work. So you really want to be liberal at using your molar masses and molecular masses, compare it to your empirical, and they should be related to each other by a whole number, right? If you see fractional relationships, that's a sign your empirical formula was calculated incorrectly. Okay. Again, the key takeaway that I want you to, and this is one skill that I want you to develop on the exam, when you're given a number 1.284, you have no clue what to do with that number. You always have an out. You take your calculator and you start multiplying by random whole numbers. Just keep going up the list until you end up with your output matching a whole number. So for example, I'd try times 5. That doesn't work. Times 6, that doesn't work. Times 7, that works. It's very close to a whole number. Does that logic make sense? And we can even check our original sign. If we take 1.284 times 14, we end up with a number that's very close to a whole number. So that's the trick. You don't actually have to memorize anything. If you're comfortable guessing with your calculator, you can find this whole number pretty quickly. Does that make sense to everyone? I know this was a relatively tricky example, but I wanted everyone to have an experience tackling these problems from start to finish and using the molar mass as an out. The molar mass is your tool to check your work. So use it, because on an exam, there's no point stressing about whether you got the right answer when you have a tool to tell you whether you got the right answer. Does that make sense? Perfect. So we're now going to move on to a relatively important chapter that's going to set the stage and help really inform your view of a lot of the laboratory experiments that we've been doing on titration. So this is chapter 5. This is solution and concentration. So we're going to be laying the groundwork to start to use these new conversion factors to express moles in terms of volume. Okay. But let's talk a little bit about, and let's refresh, what is a solution? What do I mean when I say we have a solution? So a solution, quite simply, is a mixture where one or more pure substances are dissolved in another pure substance, okay? So one species is dissolved in the other. The solute is the minor component. It's the species that is dissolved. The aqueous symbol is often a signpost that you are dealing with a solute, because what does the aqueous symbol tell us? It's a special state symbol. It tells us that we are dissolved in water. Exactly. So aqueous only really applies to solutions in water, which in this class are the majority of solutions we're dealing with. In contrast, the solvent is the major component of the solution. It's the thing that you're dissolving your solute in. So to give you a picture, to draw a picture, so suppose we have a beaker and let's draw some water. So suppose we have some beaker and we fill it with some water, okay? We then have a chunk of sodium chloride and we attempt to add the sodium chloride to our water. We attempt to dissolve the sodium chloride in water. You can even think of it like sugar, I suppose, where you can stir sugar into water. In the end, after we've mixed these two species together, we end up with a nice, clear solution. Where we have sodium chloride dissolved in water. And how do I indicate the sodium chloride is dissolved in water? What symbol do I put? Aqueous. And before, when sodium chloride is sitting as a solid, what symbol do I put? Solid, which is an S, exactly. Okay, so NaCl aqueous is describing a solution of NaCl in water. And sodium chloride in this case, is it our solute or solvent? Solute, yep. And the water, is it our solute or solvent? Is it the major or minor component? It's the solvent. It's the major component. It's the thing doing the dissolving. Does that make sense? Okay. Let's now talk a little bit about a key property of solutions. So solutions, as they are a mixture, they have variable composition depending on the amount of solute and solvent added. So just remember this idea of variable composition. When I say a solution of sodium chloride, I need to be a little bit more specific because I'm not telling you how much sodium chloride we have dissolved. A key additional property of solutions is they have uniform properties throughout. They're homogeneous. That's another way to think about this. Okay. The last main feature that we actually see and exploit in our day-to-day lives is the idea that solutes can be separated from the solvent by physical means. Okay, so let's unpack each of these points step by step. And to do that, we're going to need to draw some pictures. So suppose I have two beakers. I'm going to draw two beakers here. Both of these, into each of these beakers, I'm going to put some water. And let's suppose I'm going to put 100 milliliters of water into each. So we have water floating around, okay? So far, so good, like a typical lab setup. Now, what I'm going to do is I'm going to take a small 10-gram cube of NaCl, and I'm going to dissolve it in my first solution. Okay. Perfectly normal. We've seen that before. In the second example, I'm going to go a little bit overboard, and I'm going to add 50 grams of NaCl. In the end, I will get out two solutions. The first of which, let's count the amount of solute and solvent we have. So in the first solution, I have how much water? 100 mLs. Okay? And now my question to you is, how many grams of sodium chloride? I have sodium chloride aqueous, a solution of sodium chloride, but how much sodium chloride did I put in my water? 10 grams. So I have 10 grams of sodium chloride per 100 milliliters of water, which I'm going to assume is very close to the total volume of the solution. Okay, let's look at our second example. We would also call this solution NaCl aqueous. However, these solutions obviously aren't the same, right? We still have 100 milliliters of water, 100 milliliters of our solution to work with, but how much sodium chloride have I dissolved into this solution? 50 grams. So then, even though both of these are solutions of sodium chloride and water, do they have a different composition? Do they have a different amount of sodium chloride dissolved? Yes. Yes. I mean, on our day-to-day lives, we drink solutions that contain trace amounts of very toxic metal ions, but it's not an issue because they're so dilute. So concentration, the amount of solute, such as sodium chloride in your solvent, makes a huge difference. Okay, does that idea make sense to everyone? Now, a key feature, unpacking this further, is no matter where I sample in my mixture, no matter where I sample in my solution, whether I'm skimming off the top or pipetting from the bottom, will this concentration, will this amount of solute per solvent be the same throughout my solution? Yes. So all three of these spots have the same composition. Okay, and now for our final trick, for our final tool, let's suppose that I collect a little bit of salt water. This is actually a common method for how we commercially farm and generate large amounts of salt from seawater. So let's suppose I have a salt solution. And I just let it sit. I just let it sit for a long amount of time. The water is going to evaporate. And eventually, if I let it sit for a really long time, what will I be left with after all the water evaporates? Just salt, exactly. So then, the water and sodium chloride can be separated via evaporation. And what do we call evaporation? Is that a physical or chemical change? Physical. The evaporation is a physical change. Does that make sense to everyone? Okay. So with these basic ideas of solutions in mind, we next have to talk a little bit about how do we refer to a solution so that we're very specific on the amount of solute we have in our solution. How do we specify concentration? How do we express the amount of solute in our solution? That's our goal. So before we discuss concentration in detail, I just want us to appreciate the pictures for what happens when we dissolve an ionic solid and what happens when we dissolve a covalent solid. So let's suppose we're looking at a time scale where we have a beaker, we have some water, and then we have decided to put a cube of sodium chloride. I'm going to draw it with two colors this time because we're going to unpack a really important point about ionic solids. Okay, so I'm going to draw this nice little lattice structure. Okay, let me fill in my chlorides now. Okay, now why am I drawing two different colors? What am I trying to convey to all of you? The green is the sodium, the purple is the chloride. Now, are these atoms or ions? Ions, exactly. So this is, we have Cl minus, and then we also have sodium plus. Okay. Now, your water molecules, your solvent. So drawing out water, and we'll discuss this more in later portions of the class. I like to think of water molecules as polarized molecules. So this oxygen has a large amount of negative charge on it. So you can think of the oxygen as slightly negative, as having a little bit of anionic-like character, while the hydrogens have a little bit of positive character. Now, a consequence of this idea is that if we have a water molecule, this water molecule with its delta minus, with its negatively charged region, which ion will this negatively charged region want to interact with? The cation, which has an opposite charge, or the anion, which has a negative charge? Cation, yep. So this water molecule, the oxygen end will interact with and surround our sodium cation. So this process is known as solvation, and this interaction is an ion dipole. You won't need to know that specific term for now, but I just want you to appreciate the fact that the water molecules are interacting with and surrounding individual ions. Okay, so what does that mean? When we look, for example, when we look at sodium dissolved in solution, when we look at sodium aqueous, is it an atom or an ion that's dissolved? An ion, right? Now, in this picture as well, what do we notice is conspicuously missing? What have the water molecules effectively done when they've surrounded this sodium ion? Is the chloride ion anywhere to be found in this interaction, or is our sodium ion separated from the chloride? Separated, exactly. Now you may say, where's the chloride ion? Well, just like sodium is getting surrounded, the chloride ion is getting surrounded, except the water molecules are aligning their hydrogen ends towards the chloride. So in the end, our ions in solution, are they together or separate? Separate. And that's the key point. That's the key point I want you all to notice. When we have ions in solution, when we have an ionic compound in solution, when we think of NaCl aqueous in solution, since this is a soluble ionic compound, in reality, the species in solution are not whole molecules. What's dissolved? What do we have dissolved? But what specifically? Do we have molecules or do we have ions in solution? Ions, exactly. So when you see the symbol for a dissolved ionic compound, I really want you to think I have ion in solution. So ions are present in solution. Okay. Does that make sense to everyone? Yes.
So I know that like NaCl together are safe, but once they're separated, they're dangerous. And if they're separated,
if they're pure elements, the ions are ubiquitous. Like they're non-harmful.
Oh.
Yeah. The charge has not changed. It's just the fact you're changing an interaction between sodium and chloride to an interaction between sodium and water and chloride and water. So the solvent separates your ions and stabilizes your ions via these interactions. Does that make sense? Perfect. So that's all fine and well. Let's now compare an ionic solid to a molecular solid. And if this is one page, you know, it may seem, why are we covering this? This is probably one of the most important little sections for understanding ionic equations and understanding chemical reactions in solution. So let's now draw a picture of a molecular compound. So let's now draw another flask. Okay, so we have some water. Let's draw a little more water. So we have some water, and to that water, I'm going to add a layer of a very common solution that we all somewhat have experience with, of ethanol. It's a principal component of alcohol solutions, so CH3, CH2OH, and I'm going to try to mix my ethanol and water, okay? So after a little bit, since these solutions are miscible, or mixable, we're going to end up with a nice, clear, homogeneous solution. But what I want us to focus on in this picture, is writing out a proper state symbol and answering the question, what is actually present in solution? So when we look at a molecular compound or a covalent compound, such as CH3, CH2OH, are there any ions present in this compound? Any ions? Are there any ions to speak of in this covalent compound? Do we see any metals floating around? Nope. So then this is just going to be a molecule, right? So is it going to, can it break apart into ions? Are there any ions to break apart into? No. Okay. So once it dissolves, it's going to have what state symbol? What symbol do we use to indicate that this compound is dissolved in water? Aqueous, exactly. And the key feature of covalent compounds that are soluble in water is that in solution, do we have molecules or ions? Molecule. So the key feature of molecular compounds is that we have molecules in solution. That's not to say that water is not engaging in interactions, but we have primarily and almost exclusively molecules in solution. So ionic versus molecular compounds behave very differently in solution. And it's important that you appreciate that so we can begin to describe reactions of ions and molecules in solutions. Does that make sense? Perfect. Now that we've gotten that out of the way, I want you to save this page as we'll come back to it on a later chapter. Solubility. Solubility is a term to describe solute and solvent interactions. Quite simply, it's the maximum amount of solute that we can dissolve in a given amount of solvent under a given set of conditions. That's a lot of givens. It's mainly because solubility depends on temperature, it depends on pressure, and it depends on what you're trying to dissolve. We all know from experience, if we try to make sugar water versus salt water, it's a very different amount of sugar and a very different amount of salt that we can fit in each of those solutions, right? You also know that what we're now gonna do is we're gonna try to leverage some examples that we know from our world experience and try to describe some factors that affect solubility. So the first of which is solvent properties, and I like to use the phrase like dissolves like. So ionic compounds and polar substances dissolve in polar substances such as water. So when I say the word polar, you're primarily talking about a few major classes of compounds. The first of which are alcohols, which are designated with this OH. So for example, CH3, CH2, and let me write it in red, OH is ethanol. And as we know from our just day-to-day experience, ethanol, which is a principal component of alcohols, does it dissolve in water? Does ethanol dissolve in water? Did we do an example where it dissolves in water? Yeah. And the key reason why it dissolves in water is it has this alcohol functionality. The other functionality that I want you to know is a carboxylic acid. So the common form is CO2H. What's an example of a carboxylic acid that we've seen before? I'll give you a hint. CH3, CO2H, we titrated it in last laboratory. Acetic acid, exactly right. And we know that acetic acid, does it dissolve in water? Yes. For any other type of compound, I will tell you whether it dissolves in water or not. In general, alcohols, carboxylic acids, and any compound that is named as an acid, will dissolve in water. So what state symbol will we put for all of these if they're mixed with water? Aqueous, exactly. So an example of an acid would be nitric acid, HNO3, aqueous. So anytime it has an ending of acid, it's going to be soluble in water for all the examples that you see in this class. Now, we've talked about our polar substances. We've talked about our ionic compounds. Would someone like to give me an example of an ionic compound besides sodium chloride, something new? An ionic compound. There are many of them. Lithium chloride, sure. Sure, so lithium chloride would be another example of a soluble ionic compound. We'll talk about the solubility rules in detail and talk about rules for assessing whether ionic compounds are soluble and insoluble in a later part of this chapter. For now, in general, ionic compounds and polar compounds will dissolve in water. Now let's talk about solvents that we don't typically use in our general chemistry experience. Non-polar substances dissolve in non-polar solvents. So the best non-polar solvent I can think of are oil components. So a common component, for example, of gasoline are straight chain alkanes. We call these species alkanes, such as hexanes. You won't have to memorize your non-polar functionalities. I'll tell you explicitly if it's a non-polar solvent. But one trick to keep in mind to identify your non-polar solvents, they only have carbon and hydrogen only. So for example, C6H6, which we call benzene, would we expect benzene to be polar or non-polar following this rule? Non-polar. Yeah, so benzene is non-polar. For any of you who've worked at a mechanic shop or seen people working on cars, often the best way to get rid of grease is they use a rinse that's often very similar to hexane or benzene in terms of chemical formula. They stopped that practice as we've realized that those compounds are a little bit toxic, but that's the best way to remove grease, which is a non-polar molecule. Okay, so we have a sense of what polar molecules look like. We have a sense of what non-polar molecules look like. And let's talk about the terms that we use to describe solutions and the metrics we use to describe solutions. Okay, so the next factor that affects solubility is temperature. We can see this from our day-to-day experiences. If you've ever tried to add sugar to a really warm cup of coffee, you may notice as you wait and the coffee cools, what happens to the sugar? What do you see at the bottom? Is it still dissolved? No, right? It crashes out of solution. So a key feature of temperature is that the solubility of solids increases with increasing temperature. So as the temperature increases, what's happening at a molecular level is that collisions between the solute and solvent occur more frequently. So let's draw a picture of that. So let's suppose we have some solute. Let's suppose we have some sugar. And we have it dissolved in water. Now, what is happening at a molecular level is your water molecules are not just sitting around stationary. It's not like they're sitting around like packing material. These molecules are constantly bouncing around. And they're hitting your sugar solid, and they're bouncing off. And during these collisions, sometimes you can end up with a sugar molecule dissolving. Okay? So solubility is driven by these molecular collisions that are constantly occurring. This wall of a sugar molecule of a sugar solid is getting constantly bombarded with water from your solvent, hitting and dissolving pieces of this sugar solid, dissolving molecules of sugar into solution. Now, if this is our low temperature example, where we have a relatively small number of collisions occurring. If we increase the temperature, as we go to a higher temperature, we see a larger number of collisions. So the way that I'm going to represent that is, instead of just drawing one water molecule as our relative picture, we're going to have substantially more water molecules crowding and impacting our sugar solid. And if we have more impacts occurring, so we have more impacts, and these water molecules have more energy as they're hitting our sugar solid, will we get more sugar particles dissolved? Will our rate of solubility, will the amount of sugar dissolved increase or decrease? Increase, right? We have more water molecules hitting our solid and dissolving that solid. So more impacts leads to more sugar dissolved. Does that make sense to everyone? Okay. Now, for the solubility of gases, the reasoning behind this trend will be covered in Chem 102, but we do have a real life experience to work with here when we talk about solubility of gases. Who here has owned a fish, for example, or seen a fish aquarium? Okay. Have you ever noticed if it gets really warm, on a really, really warm day, the fish may start jumping out of the water, jumping out and almost harming themselves? The reason for that has to do with this trend of gas solubility. So let's just draw a little picture of our fish bowl. So inside our water, dissolved in our water, we have some dissolved carbon dioxide, some dissolved carbon dioxide. And we have some O2, oxygen gas, which the fish needs to breathe. So at low temperatures, we still have some dissolved oxygen and a relatively large amount of dissolved oxygen in our water. As the temperature increases, however, as the temperature increases, and at high temperatures, the solubility of oxygen drops. So we have less oxygen dissolved at higher temperatures. The other real life example, does any of you like to drink warm soda? No, right? It tastes flat. And the reason why warm soda tastes flat is there's as much carbon dioxide dissolved in the water. Is there as much gas dissolved at a higher temperature? Thinking about our trend, what happens as we increase the temperature? Does our solubility increase or decrease? Decreases. So we have less carbon dioxide, the soda tastes flat. So this is responsible for a phenomenon known as the fish kill, where at higher temperatures, the amount of dissolved oxygen drops and then fish can die off. They're in a warm pond. Okay, so does everyone get the two trends with regards to temperature? Okay. Let's now talk about one last phenomena, and that is pressure. So with regards to pressure, the solubility of gases increases with pressure. And the best example I can think of is when we're drinking soda and we have a soda can. So this soda can is under relatively high pressure. So we have some water, and dissolved in the water, the principal source of bubbles is carbon dioxide. So we have a bunch of CO2 dissolved in water under high pressure conditions, right? Now, when we open the soda can, when we open our soda can, what happens? When we open our soda can, what's happening to our pressure? You hear this characteristic click sound. What's happening to our pressure? It decreases, yep. So our pressure drops. So looking at a low pressure system, if our pressure drops, what's going to happen to the carbon dioxide that's dissolved? Will the solubility increase or decrease when the pressure drops? So the solubility increases as we increase the pressure. What happens if we drop the pressure? What happens to our solubility? Decreases. So what do we see? What happens to the carbon dioxide in solution? Does it stay in solution or does it escape? It escapes. And that's why the escaping carbon dioxide we observe as CO2 bubbles. Does that make sense to everyone? So these are just some real life examples to help you remember these trends. Okay. Another key feature to note, the solubility of solids and liquids does not change substantially with increasing pressure. since solid and liquid solubility depends more on interactions and temperature. Okay. With this established, we're next going to talk about some common words that we use to describe solutions. How do we portray and how do we convey to others the amount of solute dissolved in a solution? So we call a concentrated solution a solution that contains a large amount of solute. Okay? So an example of a concentrated solution that's sometimes generated is if we take some sodium hydroxide pellets. Did we handle a relatively concentrated solution in laboratory? What solution did you dilute up for the titrations? It was super concentrated. It's like, what solution of NaOH did we use to make our entire titrating solution? The vinegar is relatively dilute. It was the 6 molar NaOH, for example, that we used to make our 500 milliliters of titrate. So this is a really concentrated solution because we have a relatively large amount of solute relative to the maximum. So 6 molar may not seem super concentrated, but your maximum concentration is approximately 20 to 30 molar. So this is relatively concentrated. We have a lot of solute in a relatively small amount of solvent. Now, if we contrast the concentrated solution with a dilute solution. So in a dilute solution, we have a small amount of solute relative to the maximum dissolvable amount. And the best example I can think of for this is tap water. So in our day-to-day lives, we can drink tap water with no adverse effects. You can turn on the tap, drink the water, and you won't get heavy metal poisoning, right? But in that tap water, there are trace amounts of metals. So there's a little bit of copper, a little bit of magnesium, but the amount of copper and magnesium is like in the part per million. We have like 1 milligram per 1 liter. So the amount of dissolved solute is so small that the solution is so dilute that we don't often see the effects of it. There's a little bit even of sodium chloride in our tap water, but does our tap water taste salty? No. So that's an example of a dilute solution. We have a minimum amount of solute dissolved in a large amount of solvent. Okay, and I know this may seem redundant, but an aqueous solution, water is the solvent. A non-aqueous solution, water is not the solvent. You won't commonly encounter non-aqueous solutions in this course because from a practical perspective in lab, they're a little more dangerous to handle. Any questions on these initial classifications? Okay, we're now going to move into some more technical terms to describe solutions. So a saturated solution is a special type of concentrated solution. It contains the maximum amount of solute dissolved for that temperature and pressure. So what that means, and the way that you can observe a saturated solution, so let's suppose we have a saturated solution containing, so let's suppose we have a saturated solution of calcium chloride aqueous. So what this saturated is telling us is that we have the maximum amount of calcium chloride that we can fit in our solution. So if I have a chunk of calcium chloride and I go to dissolve that additional chunk of calcium chloride, will I be able to fit more solid into my solution? Will I be able to dissolve more calcium chloride if it's saturated? No, exactly right. So the key way and the key test for a saturated solution is that extra solute does not dissolve. So you have your wonderful solution, and sitting at the bottom of your solution, we'd see a giant chunk of solid. So if your solution's saturated, no matter how much solid you add, additional solid will not dissolve for that temperature and pressure. Does that make sense? Okay. An unsaturated solution, by comparison, contains less than the maximum amount of solute dissolved. So the key way that we can detect an unsaturated solution, is if I try adding solute. If I try adding more solid to my solution, will it dissolve? Yes. Okay. And we get this nice, clear solution with no solids sitting at the bottom. Perfect. Now, there's a third class of solution that requires a lot of care to generate, but you can see it, and it has quite a dramatic effect if it is observed. And the last major class is a supersaturated solution. So a supersaturated solution, as its name implies, it contains more than the maximum amount of solute dissolved for that temperature and pressure. Now, supersaturated solutions are unstable, and solid will precipitate out of solution. The solid, we have too much solid dissolved, and the solid will want to escape the solution to relieve that issue. So, a classic example of this is if you have a nice clean flask and you notice your solution looks perfectly clear. However, if it's supersaturated, so what do we mean by supersaturated? If it's a supersaturated solution, for example, of sodium acetate, then what this is telling us is we have excess solute dissolved. And if you're carrying this solution and you either agitate the solution, or if you try to add solute, you'll instantly see a dramatic effect where the solution releases or precipitates out solid to fix this saturation, this supersaturation. So you can see this quite dramatically with sodium acetate, and I would encourage you to look up a video of this on YouTube. If you take your sodium acetate, if you add solute, if you try adding solute to this supersaturated solution, you're going to see instantly that a ton of solid will crash out of solution. So you'll see a large layer of solid at the bottom of your flask as the excess solute precipitates. And the key feature of supersaturated solutions, and the key question that I have for all of you is, what do we call the solution after this precipitation process? So we've removed our excess solid dissolved, and then what do we have remaining? What do we have in this solution? Do we have exactly the amount that we are allowed to have dissolved in the solution? What do we call a solution where we have the maximum amount of solute dissolved? Saturated. So in a supersaturated solution, when they're agitated, you'll crash out solid, you'll precipitate out solid, and you'll make a saturated solution. You kick out all of the extra solute dissolved until you have the maximum amount allowed. So this is a saturated solution. Does that make sense? Okay, perfect. Now, we can express this idea in these three types of solutions in more quantitative terms. And we do that using solubility curves. So solubility curves indicate the solubility at different temperatures. And they're different for different substances, right? You notice how ammonium nitrate, sodium hydroxide, and sucrose all have different solubility curves, right? So I want you to label a few regions of the curve. So if you are above the curve, we call this supersaturated, because we have more solute than we are allowed to in our solution. If you're exactly on the line, so if you're on the curve, you're considered having a saturated solution. Whoops, one moment. A saturated solution. Because we have the maximum amount of solute dissolved for that temperature. And then finally, if we are under the curve, what do we call that solution? If we have, what was that? Unsaturated, exactly right. Because we have less than the maximum amount of solute dissolved. Okay, I'm going to do an example where I'm going to show you how to read a solubility curve, and then you'll do one on your own. So, in this first example, we're asked the question, what is the solubility of a saturated solution of ammonium nitrate at 20 degrees Celsius? So saturated, what is that telling us? Yep, I'm reading along the curve. So I'm going to go to 20 degrees Celsius, and I'm going to trace a line up. And I'm going to find the ammonium nitrate curve, which is right here. I'm then going to trace across in a horizontal line, and I end up at approximately 190 grams per 100 grams of water. Does that logic make sense to everyone? How to read the curve? You trace from the temperature up to your solubility curve for your compound, in this case, ammonium nitrate. We then trace across to the y-axis and read off the value from the y-axis. So our solubility of saturated ammonium nitrate is 190 grams per 100 grams of water. Now, what I want you to do is, using this solubility curve, I'd like you to answer the following question. I'd like you to tell me if a solution of 100 grams of sodium hydroxide in 1,000 grams of water, is it saturated, unsaturated, or supersaturated? So let's take a few moments to work on that question using your solubility curve. The solubility curve for sodium hydroxide is visible. And just take a moment to try and answer that question. Everything going okay? Everything going okay? So you go from the temperature, and then you trace up to the solubility curve of your compound. In this case, sodium hydroxide. 100. It's 100 grams of sodium hydroxide for 1,000 grams of water. And the y-axis is in grams per 100. To do a conversion. Yes, exactly. So it's 1,000 grams per 100. Oh, so it's 100 grams of sodium hydroxide and 1,000 grams of water. You're going to convert that ratio to the grams of sodium hydroxide and 100 grams. Okay. And you're essentially trying to see, is the saturation solubility greater than or less than solubility of gases? So if it's greater, then your solution is unsaturated. If it's less, it's supersaturated. If they're the same, it's everything going okay?
It's 25 degrees.
Any questions or further?
Yep. 100 grams.
Yep.
The solubility for 100 grams. Your job is to compare the solubility of your solution to the solubility of the saturated solution. Whether it's greater, less. Everything going okay?
So how much?
1,000 is like probably.
Yes, exactly right. So then you're comparing, so you read off the solubility of the sodium hydroxide. Yeah, and is that 100 greater than the 10 that you currently have to go?
Yeah.
Exactly.
So it'd be
Oh,
Exactly.
such.
Yep, it's good. Everything going okay?
It's
okay. So let's go through this one together. I saw a lot of reasonable answers. So let's talk this through. What are we doing in this problem? What is our goal in this problem? So in order to answer the question whether it's saturated, unsaturated, or supersaturated, I'm going to have to read off the solubility from this curve. So I'm going to go to 25 degrees Celsius, which is about here. And now I'm going to trace my line up to sodium hydroxide and trace across. So my solubility is approximately 100 grams of sodium hydroxide per every 100 grams of water. Okay? So this is a saturated solution. Okay? Everyone clear on how I got that number from reading the graph? I'm going to simplify this, and it simplifies to 1 gram of sodium hydroxide per 1 gram of water. Does everyone understand how I simplified that? Now I'm going to compare this solubility to the solubility found in my solution, which has 100 grams of NaOH per 1,000 grams of water. And that in turn gives me 0.1 grams of NaOH per 1 gram of water. Now, if I compare these two numbers, is the solubility found in my solution greater than or less than the saturated solubility? Less, exactly right. So then, if I have less solute dissolved than saturation, what do we call this solution? Unsaturated, exactly. So this solution would be unsaturated. Does that make sense? Now, it looks like it's 2:20, if I'm not mistaken. So we'll continue this on in laboratory.